In the 1800s, the Industrial Revolution was underway in Europe, and the populace was beginning to enjoy some of the benefits of that. The availability of creature comforts was increasing, and so were the expectations of a hard-working people. This caused growing demand for many products, not the least of which was better food, preserved by cold as it was shipped or stored. But how? In 1806, a man by the name of Frederick Tudor, an enterprising American from Massachusetts, saw an opportunity and decided to use the naturally cold climate and abundant lakes of his home state to his advantage. Tudor procured contracts with several Caribbean governments to supply them with gigantic blocks of ice from Massachusetts. Blocks of ice which he sailed to them by barge. It seems almost like madness today, but 200 years ago, it was genius. As cash began to flow, he experimented with various forms of insulation to protect his product from the ever-increasing heat as it sailed southward toward its customers. And eventually, he even managed to ship ice as far as India. After a few years, Tudor really seemed to have mastered the art of staving off the inevitable, the melting of ice, at least long enough to turn a tidy profit by shipping it to more remote regions where the demand for this phase of water was high. But even so, he was fighting a losing battle with nature. We all know that water wants to be a liquid at all but some of the coldest temperatures experienced here on the surface of Earth. And as soon as that block of ice reached 32 degrees Fahrenheit or 0 degrees centigrade, his profits began to slowly, spontaneously, and literally melt away. The weather is unpredictable, and unpredictable things are bad for business. Now, Tudor's business model, though ingenious, was not long for this world, because in 1841 a new invention came about, one which could be used to not only remove the unpredictable effects of the weather, but which could actually produce temperatures colder than a Massachusetts winter anywhere in the world on demand. Of course, I'm talking about refrigeration, that little miracle box in your kitchen that keeps food and drink cold without so much as a thought or a single block of ice being necessary. We're all familiar with refrigerators, freezers, and how they can delay or prevent the conversion of ice to liquid water. But what you might not know is that refrigerators accomplish this using a second phase, converting liquids into gases. By the end of our lecture today, we'll have all the knowledge we need to understand how this ubiquitous and indispensable technology came to be, and how the three most common phases of matter, solids, liquids, and gases, interconvert. Let's begin our discussion in earnest by considering the effects two very common conditions have on the phases of substances. Those conditions are temperature and pressure. So far, we've thought only about how substances behave at or near what we would call standard conditions, 25 degrees centigrade, 1 atmosphere of pressure. Under these conditions, we know certain materials like iron are solids, others like water are liquids, and yet others like nitrogen are gases. But iron can be a liquid when it's molten. Water can exist in all three common phases, and gases like nitrogen can even become liquids under the right conditions. So the phases of materials can interconvert depending upon the conditions. When those conditions are just right, solids, liquids, and gases change, going through some familiar and some not so familiar processes. So let's break down the effect of these two influential conditions, temperature and pressure. Start with temperature. Chemists think of temperature as a measure of the kinetic energy of molecules and atoms. The higher the temperature of a material is, the more vigorously its constituent atoms and molecules vibrate, rotate, and move within the sample. The higher the temperature, the more kinetic energy those fundamental particles will contain on average. Now, think about a solid. In solids, molecules have precious little ability to move. They can only vibrate, but they're held fast by the intermolecular forces that bind them to their neighbors. In this case, the molecules don't have sufficient kinetic energy to overcome those intermolecular forces, so we expect a given material to be a solid at lower temperatures. Now let's raise that temperature somewhat. giving those molecules enough energy to slip past one another and move within the volume of the sample, but not separate from one another completely. Okay, so now we've created a liquid by increasing the kinetic energy of molecules to a point at which their kinetic energy and intermolecular attractions are somewhat in balance. Raising the temperature yet again, we give the material enough kinetic energy to completely overwhelm the attractive intermolecular forces we discussed last time. Now we've changed our liquid into a gas. The take-home lesson here is one that I would wager most of us already know. Heating materials up causes them to change from solids into liquids, and again from liquids into gases. This trend holds for all but the most unusual and exotic of materials. Now for our second parameter, pressure. Pressure is simply a measure of how hard the atmosphere pushes in on a substance from all sides. So let's think for a moment about how pressure might affect the phase of a given substance. And if you think about it, you're actually doing a demonstration of the effect of pressure probably right now if you're sitting at home on your couch. The cushions inside your couch are made of probably a synthetic material like this one. And it's designed to respond to pressure, like most matter, by contracting. So when I place a force on top of this pile, you can see the volume is reduced. And of course, the amount of mass isn't changed. So what does that mean? Well, what that means is that when I apply pressure, I increase the density of this material until it becomes dense enough to support my weight, right? Just like when I'm sitting down on a couch. So this is a very simple relationship between pressure and density. But if we take that relationship a step further and think about it from a chemical perspective, phase changes will begin to make even more sense to us. So squeezing things makes them want to adopt a state which increases their density. I just demonstrated this at the macroscopic level with my styrofoam sample. But what about the molecular level? Of course, molecules and atoms can increase the density of a material by glomming together into a liquid or a solid, whereas taking on a gaseous phase leads to a much less dense material. So applying pressure to a substance encourages it to become a liquid or solid, while reducing pressure makes it more likely to take on the form of a gas. When chemists compile a catalog of material phases under different conditions of pressure and temperature, they create what is known as a phase diagram. A phase diagram gives us a way to illustrate and demonstrate how and why a pure substance will change phases. And it looks something like this. We take a plot of pressure versus temperature. Now, let's think about that for a moment in terms of a pure substance. How do we expect pressure and temperature to affect the phase behavior? Well, when things get cold, they tend to solidify, right? And when they solidify, they tend to become more closely packed as molecules, which means that we expect the increase of pressure and decrease of temperature to create solids. And vice versa, we would expect that if we increase the temperature of a subject at low pressure, we would get a gas. So I'm going to put my gas down here at high temperature, low pressure conditions. As we already mentioned, solids we expect to find somewhere in the area of higher pressure but lower temperatures. And of course, liquid is going to fall usually somewhere in between. But the phase diagram gives us much more information than that. A phase diagram gives us the exact condition boundaries between and among these three phases. So it tells us exactly when and how these phases will interchange. So as you can see here now, the conditions that are favorable for a solid all form a field in my phase diagram. Similarly, so do liquids and even gases. And we'll get to this little part up here in the corner in just a moment. Now, something I'd like to point out about this phase diagram is that there is only one unique set of conditions at which the solid, the liquid, and the gas can all coexist at equilibrium, and it's right here. We call this special point here the triple point. And again, it's the only place that you'll find this happens. Now, another important point is up here. We call this one the critical point. This is the set of temperature and pressure conditions at which liquids and gases become essentially indistinguishable from one another, creating a new phase of matter that we don't think about too much because we don't experience it very much here on the surface of the Earth. This is called a supercritical fluid. And we'll talk a little bit about some applications that involve these very, very special types of materials in a bit. For now, let's think about phase changes. As we cross this boundary here between solid and liquid, our sample experiences melting and freezing. Those are processes with which we're very familiar. And similarly, if we were to cross this boundary here between liquid and gas, we would be describing boiling or condensation, depending on the direction we're moving. There's a third boundary as well that we don't think about quite so much. That's down here between solids and gases at lower pressures. Now, these two phases can also directly interchange in processes that we call sublimation when we go from solid to gas, or deposition when we go from gas into solid. And the phase diagram gives us a way to determine at exactly what temperature and pressure conditions we expect all of these changes to take place. Processes like sublimation and phases like supercritical fluids may seem unfamiliar and exotic to most of us. But the truth is they aren't so unusual. The process of freeze-drying used to preserve food is actually accomplished by freezing the food down to the temperature of liquid nitrogen, then placing it under a powerful vacuum to reduce the pressure to about 1/1000th that of the Earth's atmosphere. Under these conditions, the water in the food converts from solid ice directly into water vapor through sublimation, because the pressure is below the triple point. This process not only allows for the dehydration of materials like coffee and ice cream, but also results in extremely dry products, so dry that virtually all of the water is removed. This is one of the tricks used by NASA to prepare food for astronauts. By removing all water from certain foods before packaging, the sterility, shelf life, and weight of the food are optimized for being launched into space, along with the humans who rely on it for survival. The reverse process, deposition, is commonly used to create extremely thin coatings for machine tools. Using a process called chemical vapor deposition, a vapor of carbon is deposited onto metal under precise conditions to create diamond-coated saw blades that offer the toughness of diamond without the Tiffany's price tag to go with it. Supercritical fluids are also more commonplace than you might think. Supercritical carbon dioxide is a particularly useful example. It can be created at about 50 atmospheres of pressure and has remarkable solvent properties. It can be used to clean garments or medical equipment, and even finds use in the decaffeination of coffee. Possibly the best part about it is at the end of the process, the pressure can be reduced and the solvent becomes a gas, which simply escapes into the atmosphere. So we've seen how the three common phases of matter can interconvert in response to several factors, including temperature changes, but we have not yet gotten to brass tacks to try to determine just how much energy has to change hands. We already know that every material in any given phase has a specific heat, which allows us to determine the amount of energy needed to raise the temperature of that substance by a given amount without changing phase. We covered that during calorimetry. Now, when we start and finish with the same phase, it's a pretty simple exercise to understand where all that energy goes. But what happens when we heat or cool an object to such an extent that the phase changes? The flow of energy and its effects on the molecules within the sample can be a bit more complicated. The key to inducing phase change is to give or take away enough energy for the molecules comprising a substance to either overcome or succumb to the intermolecular forces trying to hold them together. This process of overcoming intermolecular forces actually requires energy itself. So during a phase change, there is no change in the temperature of a sample. Just look at a time lapse of ice melting. Notice that as the ice itself warms to 0 degrees, there's no liquid water present at all. The molecules of the solid are simply increasing in kinetic energy, causing the temperature of the sample to increase. But at 0 degrees centigrade, as the phase change begins, we notice that the temperature holds steady at 0 degrees throughout the entire transition. This is because the thermal energy coming into the sample from the heat source is now going into overcoming the forces holding those water molecules locked in place, rather than increasing its temperature. Because the energy being added is going towards promoting the process of melting, that energy doesn't increase the temperature of the sample. But once the conversion is complete, we continue heating the liquid sample, increasing its temperature, until another phase change begins, that of boiling. And look, just as before, the temperature stabilizes as the energy input goes towards altering the phase of the sample rather than the temperature. Now, the steam, of course, in this example is escaping, but if I contain that steam and continue to heat it, I could increase its temperature even more, but only after the phase transition of boiling was complete for the entire sample. So how much heat was needed to cause those phase changes that we just saw? Well, just as we have a known specific heat for each phase of water, there is also a known heat required to melt or boil the substance. In the case of melting, we call this the heat of fusion. When we're discussing boiling, we use a term called the heat of vaporization. Of course, just like chemical reactions, these physical phase changes can go either way. So the amount of heat absorbed by water on melting is exactly the same as that emitted on freezing. So let's take a look at how these values can be used to track heat as a sample undergoes some of those familiar processes. So here's our question. How much heat is required to convert 10 grams of ice at -15 centigrade into steam at 120 degrees, assuming that we maintain 1 atmosphere pressure throughout the transition process? Well, to answer this question, we're going to need the phase diagram for water, which I put right here. And I'd like you to notice here that we've got the solid, the liquid, and the gas, and I've actually marked 1 atmosphere pressure and 15 degrees, or -15 degrees centigrade, and 120 degrees centigrade, so that we can find our locations on the plot. So what the question is asking us to do here is take a look at this diagram and find those positions on the diagram. Well, we've got 10 grams of ice at -15 and 1 atmosphere pressure to start with. That means that those starting conditions are going to be right up here at -15 degrees, and on that line I drew at 1 atmosphere pressure. Now, our finishing conditions are steam at the same pressure at 120 degrees. So I'm going to put another mark right at that location there, 120 degrees and 1 atmosphere of pressure. So heating this sample is simply another way of saying I want to move across my phase diagram, starting over here and finishing over here. So this is the trajectory that we need to follow to answer the question. But that's pretty complicated because that involves moving through 5 different regions, essentially. We've got to go through all 3 fields, plus we've got to get over 2 phase boundaries. And that creates a very interesting situation. So let's think about this here. We've got a heat that we're going to put into the system, measured in joules, and we want to monitor the temperature as we go. Why do we want to do that? Because we know at which temperatures those phase changes will take place. And if I were to plot the temperature as a function of the amount of heat put into the system, what would I see? Well, I would see this. A series of steps, actually, where those breakpoints all correspond to my initial and final temperatures, as well as the boiling point and freezing point of my sample. So, how are we going to calculate the exact amount of energy that transpires during this process? Well, we're going to rely on our old friend Hess's law again. Hess's law tells us if I calculate the energy change in all 5 of these different transitions along my diagram, that I can add them up and at the end of the day determine exactly how much heat must have moved. Now, we're going to start at -15 degrees centigrade with solid water, and we're going to heat that up. Melting is going to come next. After we have melted the solid, we're going to have to heat that liquid up from its freezing point to its boiling point, 100 degrees. Next, we're going to transition through boiling. And finally, once all boiled away, we're going to heat that boiled vapor additionally until it reaches 120 degrees. 5 different processes, all governed by different constants. Those constants are, for heating of the solid, it's going to be the specific heat of ice, solid water. For the melting, we're going to use something known as the heat of fusion. Heating the liquid will also be governed by a specific heat, but the specific heat of liquid water and the specific heat of solid water are not the same. Similarly, the heat associated with boiling the liquid is not the same as the heat associated with melting the solid, so we have a second constant for that. And finally, of course, heating the gas, which has yet another specific heat. So this relatively simple question, where we go from one point to the other, is going to require us to do 5 separate calculations and then rely on Hess's law to put it all back together at the end. So let's do that calculation. We'll begin by calculating how much heat is exchanged during the heating of the solid, then the melting, then we'll be heating the liquid, then boiling, and then we'll be heating the vapor, and finally, again, relying on Hess's law to help us calculate the entire heat change for the process. Here are the calculations that we'll have to use. Anytime we're heating the sample, we're going to be using the sample's mass times the specific heat for that particular phase times the temperature change that we need to affect to reach the next step in the process. And for our two phase transitions, we'll be using the mass times the associated heat change for either fusion or vaporization, whatever's appropriate. So let's do a couple of those calculations right now. Let's start with heating the solid. We're going to heat a solid, so we're going to need to use its specific heat. And we know that we're going to go with 10 grams, and we're going to go 15 degrees. So there's my delta T right there. Unit analysis to be sure lets me know if I'm looking for joules. I've got a good calculation here. Grams and degrees centigrade cancel. I get the correct units. I'm ready to do my math. When I do my math, I find that this is a 305 joule exchange. It takes 305 joules of heat to raise that temperature of that sample by 15 degrees. Then I reach my first phase transition. Now you'll notice that in the phase transition calculation there is no term for delta T because the temperature does not change during that phase transition. Instead of going into increasing temperature, that energy is going into helping those water molecules overcome the attractive forces that are holding them locked in that solid state. So the calculation for that's going to look a little bit different. I'll have my 10 grams times what I know to be the heat of fusion, which again gives me an answer in joules, just what I'm looking for. This calculation leads to 3,330 joules. This is the amount of energy required to melt that entire sample. And I can continue through the entire process setting up the calculations for the heating of the liquid. That's going to be governed by the specific heat of liquid water, 4.18 joule per degree centigrade. I'll be boiling the liquid, which is going to be governed by the heat of vaporization. That's going to require that I put in 22,600 joules, quite a bit of energy to boil. And then I'm going to have to raise the temperature of that vapor once I formed it yet again. So that's going to be governed by the specific heat of the vapor. In this case, that turns out to contribute 240 joules to the process. So these are all of the different energies required to put into the system to affect all of those changes that we need to simply get from point A to point B. Now it's time for Hess's law to come into play. I'm going to take those energies that I determined individually, add them together, and find my final answer. 30,655 joules of energy has to be absorbed by that sample in order to convert ice at negative 15 degrees centigrade into steam at 120 degrees centigrade. Now that we have a better understanding of the molecular processes and the energy flow associated with phase changes, let's take a look back at the topic of our initial story today, refrigeration. So, Frederick Tudor relied on the cold Massachusetts winter to create his ice. That's nice because it's free, but that process is not only seasonal, it's also confined to specific regions of the globe. Unfortunately for Mr. Tudor, engineers like William Cullen were toiling as early as the mid-1700s in pursuit of a device that would allow anyone, practically anywhere, to produce the environmental conditions needed to form ice right in their own kitchen. So one might say that the fate of Tudor's enterprise was sealed before his company ever really began. Cullen's early design consisted of a chamber containing liquid ether, which has a fairly low boiling point. The volume of this chamber could be expanded, reducing the pressure inside, causing the ether to boil. And as that happened, the ether would absorb a large amount of heat to promote that vaporization. Of course, this absorption of heat by ether would cause the surroundings to cool in accordance with the laws of thermodynamics. Next, the ether vapor was pumped into a separate chamber where it was compressed back into a liquid before being returned to the original chamber for another round of vaporization, cooling the chamber yet again. At the time, Cullen's invention was an inefficient curiosity, but it sowed the intellectual seeds used some 80 years later by famed U.S. inventor Jacob Perkins. He produced the first viable refrigeration system in human history. The technology behind Perkins' design was slightly different and more advanced than Cullen's seminal cooling machine design. He relied on principles which we'll be discussing a little bit later, but very soon. But had it not been for Cullen's ingenious exploitation of the heat flow associated with phase changes, the history leading up to modern refrigeration would no doubt be a different one. Needless to say, constructing and shipping machines capable of producing ice was a much more business-friendly model than carving and shipping large chunks of ice from colder regions of the globe. And in very short order, Perkins' invention effectively put an end to the global ice trade. So let's sum up our discussion. We started by considering how three more common phases of matter, solid, liquid, and gas, can interchange, and the influence that temperature and pressure have on these transitions. Then we took a look at a phase diagram, which is a graphical tool used by chemists to predict the phase behavior of a pure substance based on the temperature and pressure conditions that it is placed under. We noted some important features of these diagrams, including the triple point, the only conditions of temperature and pressure at which all three phases can coexist in equilibrium with one another. And also the critical point, beyond which liquid and gas become indistinguishable. This leads to a new phase called the supercritical fluid, which has some properties of liquids and others that are more like a gas. We then discussed the 6 common phase transitions: melting, boiling, and sublimation, each of which requires energy to take place, and the reverse processes, freezing, condensation, and deposition, which release energy. We saw how heats of fusion, vaporization, and even sublimation can be used to predict how much energy will change hands as these transitions occur. We also took a look at how our mastery of the energetics of phase changes led to the construction of the first ever man-made refrigerator, much to the benefit of all mankind, and also much to the chagrin of one ice mogul from Massachusetts. Over the past 2 lectures, we defined the more commonly encountered phases of matter and how they interconvert in pure substances. But there's so much more to gases, liquids, and solids and the roles that they play in our lives and in our environment. So much, in fact, that we're about to begin a series of lectures investigating the properties of each of them individually. We'll see you for that next time.